Okay, we are here at the New Otani Hotel in Tokyo, Japan. It is June 20th, 2016, and I'm Doug Fairbairn, and I'm speaking to Dr. Satoru Ito,
By the way,
correct?
I'm Mr.
Mr.
Yes.
Satoru Ito. And welcome. Delighted to have
Thank
you
you
with
very
us.
much.
Thank you.
I'm very much honored to be interviewed here.
So we are interested in exploring your career and your background, and as usual, we like to start at the very beginning to see sort of how you found yourself into an engineering and technical career. So maybe you could start and just describe something about your where you were born, your early upbringing, and what your parents did, and what kind of influence your family might have had on the direction that you took.
Yeah, I was born in Tokyo in 1944,
Right here.
right here, and I've always been in Tokyo. My family, my father was the school teacher in Tokyo.
What grade?
He was a high school teacher teaching Japanese literature.
Mm-hmm.
I am the youngest of all five sons.
Oh.
And yeah, not very much interesting in my family background, except for that I am the youngest of all five sons. And
Did your siblings pursue a technical career, or any of them?
well, the reason why I pursued this career in technology is that basically, for one thing, I like to play with things.
Mm-hmm.
I mean, device, play with. When I was born, Japan was still right after the World War.
Mm-hmm.
All the toys I had to make ourselves. We had to. So I always played with all these things, do it yourself.
Mm-hmm.
And I think that was the first kick.
Mm-hmm.
And I remember I read a book by George Gamow. George Gamow, a very famous physicist who moved from Russia to U.S.
Mm-hmm.
And he wrote many books particularly for young kids
Oh. Uh-huh.
about physics.
Mm-hmm.
And there was one book called, I think that was Tompkins in the Wonderland or something. I read the book when I was still a very young kid. I was enchanted by that book. And I think that was our first chance that when I became very much interested in physics.
Mm-hmm. And you know how old were you at the time?
I think I was still maybe 6, 7, 8 years old. Very
Already
young.
reading books.
Well, yeah, I like to read books. Very
I guess your
interesting.
father was a school teacher, so he probably encouraged such activities.
Well, I don't know. He was very diligent, serious teacher.
Uh-huh.
He was serious about taking care of other kids outside of family.
Mm-hmm.
Not very much his own sons. Yeah, I did what I like to do. Well, that was the first kick, and I studied in Tokyo all through the year, through elementary school, junior high, and high school, and entered the University of Tokyo.
Mm-hmm.
And I chose engineering area at that time.
Was the University of Tokyo engineering focused, or was it broad set of disciplines?
Well, the University of Tokyo is regarded to be, I think, one of the best, or particularly the best in Japan,
Mm-hmm.
and that covers everything.
Mm-hmm.
Laws, economics, and everything, and engineering, of course, science. And I thought I could choose either medical science or engineering physics.
Mm-hmm.
And I finally decided to choose the physics because I was somewhat interested in that.
Mm-hmm.
Yeah.
So, what year did you enter the university?
The year I entered the university was 1963.
Mm-hmm.
63, yes, 62, yeah, I think.
Mm-hmm.
Yeah. I finished master's degree in 1970 and joined Hitachi. And I spent for 5 years in the undergraduate because I spent for 1 year at Ohio State by taking off 1 year off
Mm-hmm.
at the university.
So tell me about why you decided to go to Ohio State. Why America and why Ohio State?
That was interesting. I wanted to see how U.S. was
Mm-hmm.
because I thought that Japan would be like U.S.
Mm-hmm.
5-10 years later.
Mm-hmm.
I wanted to see how it was like, and I had opportunity. There was a scholarship called Sankei Scholarship.
Mm-hmm.
Sankei Shimbun, Sankei newspaper, sponsored that program and paid full for
Mm-hmm.
everything.
Mm-hmm.
My family was not very rich, so that was very important. And,
School teachers don't make a lot of money in the U.S. nor in Japan, huh?
And 5 boys all going to
Yes.
colleges. Yeah, good
So
parents.
did you study, science topics at Ohio State, or did you just take a variety of things?
I studied physics,
Mhm.
but that was not really the purpose of going to the U.S. I
Right.
just wanted to see a U.S. what it was like.
What year were you then at Ohio State?
I was a junior year, the third year
Mm-hmm.
of
So
college.
maybe 65.
65 years in the
Mhm.
midst of Vietnamese War.
Yeah, so things were really starting to heat up.
Yeah, right. It was really a good experience for me, and I enjoyed that 1 year very much.
That must have been quite a different environment than the one you left
Yes,
from
very
the
much.
University of Tokyo.
At that time, there were very few actually Japanese people going abroad,
Mm-hmm.
and there was no airplane service, directly from Tokyo to U.S.
Oh, really?
One stop by Hawaii. So
Mhm.
that was that kind of time.
Mm-hmm.
It was really exciting. Was good. It was very good for me.
Did you tour around the United States while you were here? Or
Oh
maybe-
yeah, I used a lot of Greyhound.
Greyhound bus.
Very economic trips.
Did you make it all the way to California at that time?
Well, yeah. On the way back to Japan.
You flew through there, yes.
No, that was also very interesting. I stayed on the campus.
Mm-hmm.
I lived on campus,
Mm-hmm.
and I don't know, maybe today also, but that was a campus paper, and many students travel during the summer holidays,
Mm-hmm.
and they try to gather the body,
Mhm.
friends to go together. And one of the students he was in the doctoral course, and he wanted to go to Los Angeles.
Mm-hmm.
And he picked me up all the way from Columbus to Los Angeles.
Oh.
That was also
Get to drive across the country, huh?
Yes, great experience too.
Yeah.
I enjoyed it. Yeah. I really found that it was a big mistake with Japan that we fought against the U.S. at the time. Big country.
Big country.
Very
Yeah.
interesting.
So you got to see the U.S. and you went back to Tokyo to finish your studies, and
Yeah, I was in the third year and came back at the third year and finished the undergraduate. Then they went to a master's course.
So did the time in the U.S. influence the future direction you took, or did it just sort of
Not
fill in
particularly
your,
as my career,
mhm.
but I found that the U.S. educational system was such a excellent thing.
Mhm.
That was one very, very impressive thing.
Mm-hmm.
That was a good experience too.
Mm-hmm.
Yeah.
So what did you find the major difference between Japan and U.S. educational system?
Well, I know only about college, of
Sure.
course, but the one thing which was very impressive was the way you form the total curriculum.
Mm-hmm.
That was a big book, very bulky book, just like a telephone book,
Mm-hmm.
and listed all the curriculum,
Mm-hmm.
and you can start from the goal. If you want to take this class, then there is a prerequisite for that,
Mm-hmm.
and for that prerequisite there is another prerequisite. you can go down all the way, and that's a very excellent system.
Mm-hmm.
And you can choose and make up your own curriculum,
Mm-hmm.
and that's one thing. And the other thing is there are so many good, excellent textbooks.
Mm-hmm.
In Japanese educational system, we usually don't use textbooks.
Hmm.
And just professors just either talk or write on the blackboard.
Oh, I see. And that were your notes were.
Yeah.
Huh.
So in the U.S. system, the professors really don't have to teach.
Mhm.
Just ask questions instead. The students are expected to have studied
Mm-hmm.
anyway before you go to the classroom. So that is another excellent point, I think. And all these things are very different.
Now, has that changed over the last 50 years?
In Japan, you
yeah.
mean? I'm afraid not very much. I mean, in Japan, the educational system is that you're expected to study a lot before you enter college.
Mm-hmm.
But many students, after entering successfully to the college, they don't study anymore.
They don't study anymore.
You can just graduate, by I think attending classes for 4 years. So
I see. Interesting.
The interesting thing was that when you talk with the first-year students,
Mm-hmm.
there are many students who are not qualified actually,
Mm-hmm.
but they drop out, and after second year, third year, we can see very clearly how the students are selected and grow. So in the master's courses, most of the students in the U.S. Seemed, at that time at least, to be a lot more excellent students than Japanese counterparts.
Huh.
So that was very impressive.
Okay, so you came back to Japan and you finished your studies here,
Yeah.
and then you went directly to work
Yeah,
at Hitachi?
I joined Hitachi.
And how did you select Hitachi, or did they select you? And how did that happen?
Yeah, I thought I would either go to Hitachi or NEC
Mm-hmm.
somehow.
Mm-hmm.
And I was interested in semiconductor. I studied applied physics. I was very much interested in solid state physics. So Hitachi was one of the candidates for me, and the other one was NEC.
Mm-hmm.
And my professor, who took care of me in my graduation study, had a very good friend at Hitachi, so he advised me to go to Hitachi.
Often happens that way.
Yeah, right. I think that was okay. I mean, that was not.
So what was the state of semiconductors at Hitachi? I mean, semiconductors were still
Yeah,
relatively
I joined,
new then, and it
yeah,
was.
I joined Hitachi in 1970.
Mm-hmm.
At that time, the semiconductor industry in Japan was very premature still. We are, the timing was just that we started very serious business in transistors.
Mm-hmm.
We still were doing some germanium business, but silicon transistor was the still early stage.
Mm-hmm.
And yeah, the timing was before we started engagement of ICs and LSIs still. I think you know Dr. Makimoto.
Mm-hmm.
He also graduated from the same applied physics department at Tokyo University.
Mm-hmm.
And, he was a kind of pioneer
Mm-hmm.
at Hitachi Semiconductor operations. And I think that was about 1975 or mid-70s when we started very serious work on ICs, particularly for calculators at that time.
Well, by then you were already doing very well in dynamic RAMs, were you not?
No, not
No?
really. Still, at that time, we were working in 4K development and very early development stage of 16K DRAM. No. In 1970, we still were before that.
Yeah, Intel didn't introduce the first 1K DRAM until 71.
Yeah,
70,
that's
71.
Right, that's right, yeah.
And so the 4K must have come a couple of years
Right.
after 73, 74.
Yeah. My first job at Hitachi was my original career started as a process engineer rather than design, even though I worked in DRAM area for many years. In the first 10 years, I worked in the process area.
So during the 1970s, you were
during
in
the
process,
1970s.
doing process development? And,
Yes, yes. And particularly in the first year, the job assignment for me was to improve the reliability of a transistor, plastic mold transistor, which was a very good seller because of very excellent low noise performance for audio application. But the reliability of that device, particularly as a plastic molded device, was very, very bad. I mean, I don't know if you know, you're familiar with the term pressure cooker test.
Yes.
You know that?
Yeah.
These devices didn't pass the 4-hour testing of PCT. And, my assignment was to improve that reliability.
So what did you find the major issues to be? What areas needed change?
Change.
What needed to be fixed? What did you do to improve the reliability? To address the reliability problem?
No guideline. What I did was just to did test. As I said, about 50% failed after 4-hour pressure testing, and no other way of doing after that. So what I did was to remove plastics, just to watch the chip surface of all chips, and I did that every day for 3-4 months. And finally decided that the failed parts had some very irregular look. And that was the start. And I did all the analysis and found out a very simple thing from that point today.
Mm-hmm.
But at that time, nobody knew that phosphor was very unstable against moisture. So I found the phosphor content of that passivation film was too high.
Mm-hmm.
Very simple, but
Mm-hmm.
until
So
I found it out.
Did other companies have the same problem? Or was
that was in that particular case, we used what they called LTP, which is low temperature passivation.
Mm-hmm.
And one of the purposes of that is to avoid Fairchild planar patent.
Mm-hmm. Ah, yes.
And after fabrication of transistor, we removed all the thermal oxide and deposited new passivation film after that.
Mm-hmm.
And phosphor, as you know, was the very key ingredient to stabilize the surface.
Mm-hmm.
But nobody knew the content of phosphor was so critical. And until the time I came to the conclusion that that was the reason, the problem.
Mm-hmm.
It took a really long time, but I found it. I made a complete, not really complete, a very drastic improvement
Mm-hmm.
the reliability. I worked almost for 1 year
Mm-hmm.
to change all the basic ingredients of new passivation, and that formed a very basic career for me actually. And starting from that point, I worked for about 10 years, starting from transistor, then analog ICs, LSIs, and finally I worked on improvement of plastic molded microcontrollers and memories.
Mm-hmm.
And at about that was about 1980 when it came up with the plastic molded, what I call high reliability 16K DRAM.
Mm-hmm.
And also 8-bit microcontroller, and we went into Delco and IBM, and that was the second challenge I think I had. I was assigned to get qualification of 16K DRAM, which was actually 32K piggyback DRAM
Mm-hmm.
for IBM.
They call it
mainframe.
Caribou?
Caribou, yes.
Uh-huh.
I worked on the Caribou program, and
You had one dip package on top of the other, right?
yeah, at that time, Intel, Mostec,
Mm-hmm.
and these guys were the suppliers of the ceramic packages.
Mm-hmm.
And we went into IBM, and plastic was as good as ceramic. It's very low cost, and it took almost a full 1 year to
Mhm.
get qualification.
Mm.
I stayed in Boston to get that qualification. Was very, very challenging, interesting program I had, and I don't know, because of that success, maybe I was transferred to DRAM operation after 10 years of process development, and became a manager in DRAM operation.
Mm-hmm. And that involved the design as well as the fabrication?
Yes. At that time, we had a memory department, and within that department, there was one DRAM division and other memory division like SRAM and EEPROM. And I became in charge of DRAM.
Mm-hmm.
That was still at the time of 16K DRAM, as I said. And that was the start of my career in DRAM. So I worked in DRAM and later, including all memories, in memory area for about 10 years after that.
Now, that was about the time, I forget exactly when, but when Intel decided to get out of the memory business, right?
Yeah.
Was that
When I
during the
started
time?
my DRAM career, Intel was still, of course, a very major supplier.
Mm-hmm.
And yeah, it was about 1980, I think, when Intel decided to move out of DRAM.
Did that come as a big surprise?
It was a big surprise, but starting from 16K was just the beginning for us as a real serious business starting DRAM.
Mm-hmm.
But by the success of that generation after 64K, particularly 256K, Japan was already a very major DRAM supplier, occupying a very major share.
And that was largely because of the tremendous yields you were able to attain,
I think
and
that,
the
yeah.
low cost that you could.
I think, yes, that's right. Cost and quality.
Mm-hmm.
And,
Right. Americans didn't believe that you were getting the yields that you were.
Yeah, yield was, of course, the key. And of course, also the success in very high reliability plastic devices was another
Mm-hmm.
a key thing. Intel, most of the other people in the U.S. at that time was still working in ceramic and sorted packages,
Right.
which were a lot more expensive in terms of cost. And quality, reliability we are pursuing for after was, I think, was very, very good.
Mm-hmm.
Yeah. We made big success, as you know.
Mm-hmm.
I worked in DRAM area starting from 16K through 60 meg.
So it seemed that the Americans just didn't believe that you could attain the yields that you were seeing, that it was that perhaps they didn't even try hard enough because they didn't think it was possible. Whereas the Japanese seem to have always said, we can always do better.
Well, yield is of course a result.
Yes.
There are all kinds of things which are involved in that. And one very important thing at that time, particularly in Japan, was that we worked very, very closely with material suppliers and equipment suppliers.
Mm-hmm.
And most of the semiconductor equipment suppliers today are U.S. players.
Mm-hmm.
But at that time, in terms of new technology, still U.S. of course was very much advanced. But the equipment technology which were related with manufacturing, actual manufacturing,
Mm-hmm.
The very close tie, cooperation between semiconductor suppliers and equipment suppliers, and also material suppliers.
Mm-hmm.
I think that was very, very strong competitiveness.
Mm-hmm.
Of course, in order to raise high yield, the discipline of operators and all the things are very important.
Mm-hmm.
But together with that, I think equipment and material technologies was the key.
Mm-hmm.
The bad thing was that we worked with all these equipment and material suppliers at that time, and these players grew. I mean, through that activities. But I think one of the reasons why Japan became not very competitiveness after a certain period of time was because of the transferring all these technologies, particularly equipment and material, which were grown together with us, were all developed, overseas, and became a very, very important key technologies for new players like Samsung and all these guys. And,
they all benefited from the work that you had done.
I think so. Yeah. Really, that was one of the keys, I think, at that time. The cooperation between the semiconductor suppliers and material and equipment suppliers.
Certainly allowed the Korean industry to ramp up very rapidly.
Oh yeah, that was. I think they owed a lot.
Sure they do.
To these activities we did.
So, you then moved to the DRAM. Tell me about the Caribou program and why that was so important.
Well, that was so important because DRAM business overall was still an infant business for us. And getting into IBM and adoption by IBM mainframe, which was the really important market, was that drove our business really, and that was the real major start of our DRAM business, and the success of that, the qualification of plastic molded 16K or 30K DRAM was so important.
Did you sell the Caribou product to other companies, or
no? That was
just an IBM product,
proprietary thing, and soon after that we shifted to 64K. IBM was of course a mainframe supplier long before launching PC yet, so. Very conservative company in terms of technology. So, but other customers, particularly in Boston area, like Wang, Dick, and these people came up, and they were the major customers for 64K to 56Ks. And we all got kick in U.S. business, and that drove our business.
So you managed the whole DRAM activity until when?
I started to be engaged in DRAM in 1980, and from 1980 through 1985 or 6, I was a dedicated DRAM manager, and after that I became in charge of all memory business. So in terms of DRAM, that was about 5-6 years. And 1 megabit DRAM development was very exciting program. Hitachi was a leader in general, not particularly memory, but in microcontrollers and system SIs, the Renesas Technology. I think you will interview Dr. Masuhara. He worked in CMOS technology quite a bit, and we applied CMOS technology to DRAM as the first player, together with Toshiba actually. And Toshiba was a good competent company. And together with between Hitachi and Toshiba, I think DRAM was shifted totally to CMOS. And all the DRAMs at that time, of course, was NMOS. And shifting from to NMOS to CMOS was a big move. It was a very challenging project, I remember.
NEC was also a big supplier then?
Yeah, NEC always was a big supplier in semiconductor in general in Japan, but particularly in DRAM. Of course, they were one of the major suppliers, but they were very strong in NMOS technology. But in terms of CMOS, Toshiba and Hitachi was kind of pioneers. And after that, I think Hitachi, Toshiba competed very much. Yeah, we enjoyed that competence.
So then you switched over to the microprocessor area.
Yeah, after that, I was moved to what we called Device Development Center, which is one of the organizations within the semiconductor operation, Hitachi. And I really didn't know anything about ASICs or microcontrollers, but somehow I became in charge of all the management of that operation.
You had people that did know about those things.
Yeah. So Kihara was one of my good friends, and he was the guy who worked in SH microcontrollers, RISC controllers, and what I call H8 microcontrollers. Together with DRAM operation, Hitachi was very major competence was in microcontroller. And I worked with all these guys in those areas.
So you moved over to the microprocessor area in 86 or 87?
I don't know, but maybe Makimoto-san was one of the guys.
And what was the... had Hitachi already adapted or adopted some RISC ideas in terms of implementation of those versus CISC? What can you tell me about that evolution?
Hitachi started the microcontroller business by introducing Motorola's technology and products at the first stage. And we worked with Motorola for many years in very good relationships. But after working with in that relationship for several or many years, there was a very severe dispute between Motorola and Hitachi in terms of IPs and patents. And Hitachi was sort of forced to move out of that Motorola team. And we decided to develop our own proprietary architecture, which we started as H8 CISC architecture microcontroller, starting at the first stage as 8-bit, and moved into 16-bit. But in the course of that development, the RISC architecture started more or less as a main application workstation, all these things by HP and these people. And our territory was a real-time controller, rather than workstation kind of microprocessors.
Right.
So we had all kinds of big discussions and decided why not applying that technology in microcontroller. That was the start of RISC architecture microcontroller, which we called as SH.
Mm-hmm.
And we made big success in that. We started first as a 16-bit, but internally I think that was 32-bit architecture. It was a very, performance-wise, that was still one of the controllers which other players also supply.
Mm-hmm.
But in terms of power efficiency or code efficiency, I think the SH was the best at that time.
Mm-hmm.
And we made a big success in that.
So to be successful in that, you had not only to supply good silicon, but you also had to supply design tools, compilers, and other things to go with it, right?
Well, as a as a part of microcontroller business, of course, we did all these things. But we of course worked in compilers and all these things. But our major competence was actually SH, chip architecture, and hardware.
Okay.
Basically, we worked with some game players, or I worked a lot with Microsoft too. But that was the timing when mobile phone shifted to digital from analog architecture, and Nokia, of course, was the leader at that time.
Right.
And we competed with TI in Nokia digital mobile program.
Mm-hmm.
And TI was a very strong DSP supplier
Yes.
at the time. And so TI chose ARM as a controller itself.
Right.
And combine that with their DSP. And that was a big defeat against TI, that we lost the Nokia business.
To ARM.
To ARM.
Through TI, right?
Through TI.
Yeah.
And
Yeah,
that was
it could've
actually
changed-
one of the biggest reasons why ARM became so successful.
Change history.
Yeah, change history. If that had not been the case, the picture would be different. Yeah.
You know, the people at ARM, really Acorn at the time, designed the ARM chip using VTI's design tools.
Right.
And
Yeah, ARM was the real successful IP supplier. And their business model at that time was very, I would say very revolutionary business model. And they made a big success.
I interviewed in this way, did an oral history with the two primary designers of the ARM chip. And one of the things that ARM is, of course, well known and been successful because it's so low power.
Right.
And so I asked them what they did to keep the power so low and how they managed to do that. And they had two answers. One was they knew they wanted to put it in a plastic package, so they wanted to get the power as low as possible. And so they paid a lot of attention to that in terms of just trying to minimize it. But at the time, there were no design tools to tell them, you know, how much power they were going to use and that sort of thing. So they just always sort of made the transistor sizes as small as they could. And the other factor they said was we only had a very small design team, like 4 or 5 people. So the design had to be very, very simple.
Mm-hmm.
And so those are the two constraints, small design team and go in a plastic package.
Mm-hmm.
And it ended up being, the power ended up being like 10% of what they had forecasted, but they didn't really know
Mm-hmm.
what it was. And it wasn't, it was only a goal because it had to go in the plastic package. It wasn't a, you know, and this was, they were designing it to be a processor for a computer, you know, for the next generation Acorn workstation. It was only later that it got applied to embedded processor, and, you know.
Yeah, at the very
So
early stage, yeah, right.
it was sort of an accidental outcome of the development, and partially driven by the fact that they had a very small design team, so they had to design a very small processor because that was all the resources they had.
Very, very interesting. Yeah. But in terms of chip performance or you know, low power performance and all that, I think SH and ARM were very similar.
Mm-hmm.
The one big difference was that we were the hardware supplier,
Mm-hmm.
and we kept all these things as a proprietary chips and technology and everything.
Yeah.
And ARM, at the very early stage, decided that they would be a IP supplier instead of a chip supplier.
Right.
And that was the biggest difference, I think.
Mm-hmm.
Yeah.
That was not an obvious decision at the time.
Oh, yeah.
Nobody else was doing that. Well,
Yes.
interesting. So had Hitachi studied sort of the RISC idea was relatively new and somewhat controversial at the time.
Of course, yes. Everything is different, and the biggest difficulty, of course, is how to get customers accept that.
Mm-hmm.
You know, all the customers familiar with the CISC architecture and development environment and everything,
Mm-hmm.
compilers, and so that was a big gap between that. And applying that RISC architecture to a controller world was very new at that time.
Mm-hmm.
Of course, ARM was already working on that, but they were, as you said, at the very early stage, worked primarily as a computer, a microprocessor rather than a microcontroller.
Correct.
So that was a challenge.
Mm-hmm.
But, I think Hitachi did a very good job. I was not a real hands-on developer myself. I was rather in a management position at that time already. So Kihara-san knows that very well. He was in the heart of that development.
So who made that decision to go that direction? Was that a management decision? Was that engineering?
Yeah, I think so. There were several key people, including Kihara.
Mm-hmm.
And Makimoto-san was the real key person at that time, deciding all these new architecture decisions and everything.
Mm-hmm.
Yeah.
So what was the next stage? How long did you continue in management of the microcontroller?
I worked in that area for 5 or 6 years, I think. I don't know if I was really an engineer or not, but I was assigned in many different areas, managing sales and controlling manufacturing, all these things. Then I was moved to Europe and the U.S. To manage the branch companies there. So as a real engineering work, I think I worked for starting from 1970 through 1990, I would say, about 20 years.
Mm-hmm.
And then after that, I really moved to management positions.
Mm-hmm. So, did you? So your next step was to take on the Renesas.
Yeah, after I worked in Europe for 2 years to manage the factory there. Then I went to US for 1 year to manage the sales operation there.
Mm-hmm.
And after I came back, right after I came back from US, I, together with other people, started to discuss about joint project
Mm-hmm.
with Mitsubishi,
Mm-hmm.
and started Renesas Technology in 2003.
Mm. Where was getting back to Europe, where was the factory, Hitachi factory in Europe?
In Europe, at that time, the factory was Semiconductor factory, and that was in a city called Landshut, near Munich.
Mm-hmm.
And that was originally a DRAM factory in Europe.
Mm-hmm.
But because of the DRAM downturn, we had to shift from DRAM to other operations. So I was assigned to do that.
Must have been very difficult. Something set up for DRAM is not optimized for logic, no?
Yeah, that was a good experience though. And then I moved to US.
Mm-hmm.
And when I was working in US, the prime time of DRAM for Hitachi was over already.
Mm-hmm.
And I thought how Hitachi Semiconductor Corporation should be. And I was not in the position to decide that anymore. But in my mind, I decided that Hitachi would focus on microcontroller.
Mm-hmm.
And after I came back from US, I talked with Dr. Nagasawa, who was in charge of Mitsubishi Semiconductor operation at that time. And why not getting out of the parent company and form the new company? We decided to try to join.
So the reasons that Japan fell behind, they didn't fall behind in technology, correct, in terms of DRAMs, but in terms of investment level or cost, what were the real driving forces in terms of?
I think in 1980s
Mm-hmm.
and at least first half of 1990s, for about 15 years, Japan led the business in DRAM because of technology.
Mm-hmm.
Technology competence was the very pure reason why Hitachi, Japan,
Mm-hmm.
was so competitive.
Mm-hmm.
But after that, the technology, as I said before, through equipment technology and material technology,
Mm-hmm.
it became kind of global, I would say, infrastructure
Mm-hmm.
instead of proprietary thing. And technology could not be the core competitiveness
Mm-hmm.
anymore. The core of competitiveness became more of the business decision, investment decision, all these things.
Mm-hmm.
And I think Samsung was very excellent in making up strategy
Mm-hmm.
in that kind of environment. And Japanese suppliers, including Hitachi, I would say failed.
Mm-hmm.
in making right decision in right timing.
Mm-hmm.
And of course,
Would they have needed to make bigger investments sooner to?
The difficulty at that time was, as many people say, investing in semiconductor, or particularly in DRAM,
Mm-hmm.
was very risky. I mean,
Yes.
if you fail in timing or in scale, the damage would be very, very big. So,
Right.
From the point of view of a more or less conservative company management culture, like
Mhm.
Hitachi, Toshiba, all these
Mm-hmm.
Japanese players, that decision was actually very difficult, I think.
Mm-hmm.
And particularly Samsung, even though they were already a very big company,
Mm-hmm.
still it was more or less the ownership company.
Mm-hmm.
Yeah. And they made a very, very right decision, taking a risk. And the timing they invested was at the time of downturn. And in terms of timing, that was the right timing, of course.
Right. But very difficult to make.
Very difficult. But for Japanese companies, most of the Japanese companies, that was a difficult decision. You
Yes.
know, starting investment at the timing of downturn when we are making lots of negative figures.
Yeah.
So
Difficult
that
for
was
any
one
business, and yeah. And
So-
the cost of building factories was escalating.
So I think what happened was instead of technology leadership,
Mm-hmm.
the strategic and management leadership became the core of competitiveness. And I think that was one of the biggest reasons why we lost.
Mm-hmm.
Yeah.
So tell me about, so how did you move to, well, did you realize that that was a problem at the time? And did Renesas, was it set up to address that problem?
Yeah. Hitachi DRAM operation was spun out from Hitachi
Mm-hmm.
and joint company with NEC was
Mm-hmm.
formed as LPDER. First Hitachi NEC Memory, then became LPDER. And so when I came back from US, DRAM was not Hitachi business anymore.
Mm-hmm.
And well, I thought what would be the future picture for Hitachi Semiconductor operation.
Mm-hmm.
And microcontroller was, together with DRAM, before, several years before that time, was the core competence.
Mm-hmm.
We were already a very major player in microcontroller.
Mm-hmm.
And there were actually three major microcontroller players at that time. I think Hitachi, NEC, and Mitsubishi
Mm-hmm.
at that time. And I thought to become a real major player in the microcontroller, I thought it would be necessary for us to make some bigger joint venture.
Mm-hmm.
And joining with NEC was very difficult because we were competing too much at that timing.
Uh-huh.
So I thought the Mitsubishi would be the right choice, and came back and, as I said, I discussed with Dr. Nagasawa. And we agreed between us, okay, why not try?
Mm-hmm.
And I think forming Renesas was the right decision.
Mm-hmm.
many things happened after that, but still, making that company at that timing was the right thing to do.
And how did that turn out immediately? What worked and what didn't, as far as that? What went well, what went as you expected, and what didn't?
After
you combined
Renesas,
them,
I would say at the start, after 4 or 5 years, things went on the right track, I think.
Mm-hmm.
But where I think about it, think it over, one of the problems that was my fault partly, or a major portion, was the lack of focus.
Mm-hmm.
We got out of memory business overall, and as Renesas, and we focused on microcontrollers, system size, and all that. But still, we covered almost all semiconductor areas except for memory.
Mm-hmm.
And that was not enough as a focus.
Mm-hmm.
And as you know, after that, NEC joined in that venture again, and Renesas Technology became Renesas Electronics between Hitachi, Mitsubishi, and NEC. And in the last a few years, Renesas converted, made a big shift to make a very strong focus to microcontrollers, and particularly automotive business.
Mm.
And that was a very right thing to do. We should have done that sooner, I would say. We focused to non-memory business in that sense. That was the focus, but not enough.
The right direction, but not enough.
Yeah.
What was the last size? What size of DRAM was the last one that Renesas did?
The last one, that was, I think, 64 meg DRAM before Peter started, I think.
Mm-hmm.
I was engaged in memory business until 60 meg, and after that 64, maybe 256 meg.
Mm-hmm.
I was away from DRAM business at the time, so I was not very sure, but
Mm-hmm.
I think 64 meg, 256 meg, they were handled at Tita, I think.
So, just to then finish, did you retire from full-time management from Renesas? What?
Yeah, 2008.
Mm-hmm.
When we started Renesas, I took the position of President and COO, and
Mm-hmm.
Dr. Nasawa was the Chairman and CEO. And I became a Chairman CEO after that.
Mm-hmm.
And in 2008, I retired.
But still an advisor.
No.
No?
I worked as advisor for a couple of years, but
Mm-hmm.
now I'm completely retired from that.
Mm-hmm.
I
And
do
so,
many things without making any money.
Yeah, still busy, but not making money. So you mentioned STEQ, S-T-E-Q. Where is that?
Oh,
Oh.
STEQ. Oh,
Yeah.
yeah, STEQ, yes.
Oh, S-Tech.
I started a venture with the name of STEQ
Mm-hmm.
with a friend of mine.
Mm.
And I worked in, I think that's now fourth year now. We're still struggling.
An investment company, like a venture investing company?
No. Yeah, we have investors, two big investors, but not venture investment company. No.
Mm.
That company is doing LED lighting module.
Mm-hmm.
Module technology is the
Okay.
core, basically.
So, in general, I guess, Japan is still, I don't know what the right way to describe, is struggling or, not having the kind of success that it did previously, and semiconductors in general, and to some extent others. What do you have ideas as to what needs to, well, first, do you agree? Is that a proper characterization? And secondly, do you have your own ideas or recommendations as to what might need to change to improve the situation?
In semiconductor or?
Well, in semiconductors and maybe just broader technology. I mean, there's so many different, the opportunities are exploding in so many different areas. And
Right.
I may not characterize it fairly because I'm not close to the situation, but my sort of general perspective is that Japan was a clear leader in, semiconductor and electronics technology. During the 1980s, the U.S. thought Japan would beat everybody. And the world continues to change. The Koreans, the Chinese, and the explosion in new applications and new technologies and focus on software and social media and so forth. And what's your?
I think the first, as in the area of semiconductor.
Mm-hmm.
Japan is not really a leader anymore,
Mm-hmm.
but still can be competitive,
Mm-hmm.
competitive enough to add value
Mm-hmm.
to the industry. One of the problems we had in Japan, one of the reasons why we failed,
Mm-hmm.
so to speak, was that we kept a general supplier for too long,
Mm-hmm.
and world industry changed at the very early timing to be dedicated special player,
Mm-hmm.
and all the successive players are all dedicated player
Mm-hmm.
in some way.
Mm-hmm.
Intel, of course.
Mm-hmm.
Most of the successful players were like that. Even TI is
Mm-hmm.
now, instead of being a general semiconductor supplier, they are, I would say, analog company.
Mm-hmm.
And Infineon became a power device company. All the semiconductor suppliers in the world are in some way dedicated in some special area.
Mm-hmm.
And in the last 3-4 years, Japan finally got to that point, more or less.
Mm-hmm.
Renesas is now a automotive, microcontroller, real-time controller business.
Mm-hmm.
It's a very clear dedication right now. And Toshiba is a dedicated flash memory supplier.
Mm-hmm.
And Sony is an image
Mm-hmm.
sensor supplier.
Mm-hmm.
And in that sense, I think we are now in some management system which is, I would say, global standard.
Mm-hmm.
And each of these companies has its own competence. I think Renesas is strong enough to in that specialized area today, and Toshiba, of course, and Sony is almost covering most of the worldwide share in image sensor.
Mm-hmm.
So pursuing that way more and more clearly, I would say Japan would be okay. I don't think Japan would dominate
Mm-hmm.
the business anymore
Mm-hmm.
as we had done some time ago
Mm-hmm.
in a very special DRAM area.
Mm-hmm.
But pursuing this way is on the right track, I think.
Mm-hmm.
The thing we need to think about is we are still not very good at imaging long-time future.
Mm-hmm. Mm-hmm.
Japanese way of thinking is more like continuous, continuity rather than
Mm-hmm.
jump.
Right.
So,
Well, I don't think any established company is very good at envisioning the future. It's the U.S. has been, its success has come from its ability to, form new companies to pursue new things. The established companies are never the ones to pursue new areas, right? I don't care whether you're Japanese or American, or you can't change, you can't move fast enough to
but I
adapt.
think that's the strength of U.S. I mean,
Mhm.
that's a combination of big established companies and the new ventures
Mm-hmm.
which create a new future. And a very good combination of these two, creating competitiveness of U.S. Industry overall. But in Japan, we are still not very good at on this side.
Mhm.
Growing new ventures, envisioning the future. But I think that's also starting.
Mm-hmm.
The problem we have is that we do not have good venture funds
Mhm.
still. So even though there are good ideas and good young people there,
Mm-hmm.
not enough monetary support yet, I would say. But
Yeah, it requires full infrastructure in terms of
right.
the whole startup culture. The museum has just launched another center I didn't mention called Exponential, which is focused on entrepreneurial activity and sort of studying, documenting, and celebrating that culture. And we've been putting together for some time and working with a lot of people that have played a significant role in that. And it's a very complex web to kind of put all the pieces together to make it happen.
Right.
In terms of envisioning the future, as part of doing this, we were celebrating some people who have made contributions over a long period of time in the entrepreneurial area. And so an obvious one was Gordon Moore. And so I hadn't heard this, and all the things that have been written or whatever, I hadn't heard this particular story, but we were videotaping him for one of the sessions, and he had come to the museum a couple of weeks ago, 3 weeks ago, when Andy Grove had died. There was a memorial service at the museum for Andy, and people came from everywhere. And so Gordon came for that, and a couple of weeks later after that, we were also having this announcement gala. In fact, I'll send you there's a videotape of this sort of announcement, and it includes, you'll find it interesting, but when we were interviewing Gordon Moore for this, he made the comment that when they had, at Fairchild, when they had finally kind of figured out how to make the integrated circuit, the first time, and how to put the pieces together and get it somewhat reliable and manufacturable, they sort of sat back and said, okay, we did that, what's next? And here they had created, the basis for 50 years of explosion of technology, and they had no idea what they had created. It was, okay, we just did that one thing, now what's the next thing to do? And so Jay Last, who was one of the people that had formed Fairchild, one of the traitorous eight, said that was one of the reasons why he left Fairchild, is because they didn't realize what they had in terms of the integrated circuit. And I thought, here's the ultimate invention of the 20th century, and the people who did it had no clue as to what the impact of what they had just done. It was just, okay, we did that, what's next? And so, and that is so common, people, it's so hard to understand the impact, and some people have to, so yet another company many companies spun off of Fairchild to go make and obviously Fairchild continued to advance that technology, but at the time that they created it, very few people understood that they had just created the greatest invention of the 20th century, and they were only asking what's next. So anyway, it's envisioning the future is planning the future, whatever is. And there have been many other instances like that. It's very hard.
Yeah,
and
Japan
you need
is very strong in competitors. As far as the future is envisioned. I mean, very strong in automotive business area. And that's everything is continuous. I mean.
As long as the future is incremental, then you can
Right.
you know how to do that, right?
Right.
But when the future is discontinuous, you need that entrepreneur, that one
Right.
person to go off and just do it, right? And the one who sees what that is. But very few established companies can.
The great America is that you're successfully establishing both sides of it. I mean, jump in continuity. Japan is very good on this side, but we still need to do something about this side.
So anyway, that's you're not the only one struggling with trying to figure out what's next.
What's next?
What's next is very hard to very hard to predict.
Makimoto-san, by the way, is a very good visionary. I mean, so he envisioned many good things like SH, H8, and all these things, and we need to do that.
Well, perhaps we're winding down. Do you have any other thing that you'd like to add as part of the?
Well, no. Thank you very much for giving me this opportunity. I'm
Mhm.
very honored. And,
Well, we are honored as well, and thank you very much for
Thank you very
taking
much.
the time. And we appreciate all the help that you've also provided in lining up the other interviews. I think the selection of candidates has been excellent.
Thank
It's a
you very
very
much.
broad cross section of some very people who have made significant contributions, each by their own path.
Yeah, I think the
and-
selection this time was good. I think.
Yeah, I'm very impressed.
And
So
Tani-san helps us
make it
quite a
happen.
bit.
So anyway,
Thank
thank you very much.